our next presenters are Team 12, Speaker Position Tracking. The customer is Professor Bill Hauser, who's actually in the Mechanical Engineering Department here at Boston University. With that, I'll present Team 12.
Hey, so we're Team 12, the Smart Cam team, and as mentioned, we are working for Hauser, who has hooked us up with the distance learning program. Basically here, they stream lectures over the internet for remote students, and they have a little. Previously, they had a little controller to control the camera, a Sony camera you can see at our setup. It was manually controlled, and we want to make it automatic so that this guy controlling the camera can do less. He also has responsibilities of fielding questions and making sure that things are going smoothly. So having an automated system would make this a lot easier for him. It would also enable professors to hold office hours without having the paid student be there to film. So we're not given concrete requirements for this, so we kind of established this ourselves. The system has to be able to interface with the camera, which takes VISCA commands, which is, I believe, Sony proprietary way of talking to the camera. It's got to decode the frame within 33 milliseconds for processing. We want it to make the decision to move within half a second. We also want it to run smoothly. We don't want it to aggressively track like one-to-one motion. It should look natural as if being filmed. It should also account for blackboards, so it should include a blackboard in the frame if it believes, if we determine that it's relevant to the lecture.
So this is our full functional block diagram of our system. As you can see, we have a video input coming into the system. We capture it, so we convert the analog signal to digital. We take those raw video frames, we pass it to some vision analysis code that will find the presenter, output an XY coordinate of where he is in the frame. And as part of the vision analysis, we then also take the XY, where we are in the room position, the room information, and we will come up with whether or not we need to move the camera. And from there, we will pass that to a control mux that will take those movement commands and actually translate it and talk to the camera. In addition, we have a GUI, which we'll talk about later and show. That's a website. And the GUI interfaces with the entire system. It can control parameters, it can turn on and off the system, it can manually control the camera, it shows a video feed out, and that's among other functionality. So we can actually split this up, and it is split up into actually 3 separate programs. In green, we have the real-time vision analysis code that runs around 24/7, or whenever the system is running. It handles all the capturing of video and all the vision analysis. We have the control program, which is initialized and it's run as a system service that actually opens up connection to the camera. It initializes the addresses, and it deals with all communication with the camera. So there's an interface to talk to it, and it deals with translating it to the proprietary VISCA commands. And for our GUI, we use Apache, and we have a PHP website with various other services. And to glue all these together, we use an amazing key value store called Redis. If anyone does need software work and you need some sort of key value store, I recommend you use it. It's insanely fast. It's something like 50,000 operations a second. And it's completely single-threaded, and all operations are atomic, so we can easily pass data between modules without any issues of race conditions. And it makes it very easy, and it's very low overhead. It's a nice plug for them. So, small breakdown of the system. We'll start with the capture card and vision analysis. Specifically, we have this camera, the Sony EVI D70, which needs to go to the capture card. For our purposes, we're using the Blackmagic Intensity Pro, which can just about input and output every single non-professional format. We are only using Compositor S-Video because that's what the camera outputs. We then take those raw video frames, pass it to, or it's passed our capture software module, which then takes those, converts to color space, to one usable by our vision analysis code, and then packets it. It comes into our vision analysis code's format. We're using OpenCV, so it's an IPL image. Then we pass it in vision analysis. Let's talk a little bit about these. We use the proprietary API to open the capture card. We can set a number of properties. As mentioned before, we can input just about everything from 3D 60 hertz HD video to lowly composite. So we're just using composite S video. We're not using any sort of audio because we don't receive any audio from the camera. And after initializing that, we pass it on the raw video frames to a color space converter. So unfortunately, when we capture composite, we can only take in raw NTSC video in the YUV color space. However, OpenCV represents RGB. For those of you who don't know, YUV is a different way of representing video. Y is luminance and UV is chrominance. And Y can be thought of as saturation and brightness, and U and V represents the color. And it has a number of formats for compressed video. Specifically, it takes human vision into account, and when you're transferring this video data on open line, you can provide less color data on the line and save bandwidth. However, it's not very easy to use for us computationally. Instead, we want to convert to RGB, which most of you are probably familiar with. It's color additive. And luckily, both of these can both be mapped to a cube, and the conversion between them is linear. And in memory, the field, it's a very regular data structure, so just by applying some simple equations, you can convert between the two. Pass it off to Peter.
So the vision analysis component, basically our goal is to track a single presenter, and the assumption is there's only one presenter giving a presentation. So with that as our goal, we want to remove the dependence on color thresholding, because he can be wearing any type of shirt, any color, any color shirt, so we don't want that sort of thresholding to take precedence over whether he's moving or some other components. So, and again, there's lighting changes that can happen, and that makes tracking, blob filtering, other basic thresholding techniques somewhat difficult. So instead, we want to handle many track points of interest, and we want to measure the object position change so we can pass the XY coordinates to the control system. So we use pixel tracking and optical flow to assess where the person is. And basically, there's a lot of tensor math and other complex things involved. But essentially, we want to look for a salient point or some contrasted pixel with surrounding pixels leading to it with some local gradient. And that part will move because the presenter is obviously moving around, and those dark pixels that compose him will go to a new location. So we want to draw a vector from the original location to the new and report that pixel's location. So again, we use OpenCV, so that comes with a function that basically says calculate this optical flow, and we use the Lucas-Canad function, which does that for us. So these points are tracked, and we get that XY position, and we can report the centroid of all those collected points. And this is basic tracking of my hand in the frame. If it moves, it looks at the really salient regions of the thing that's moving, which is usually edges, because there's a high contrast.
And from this image where we determined the motion of the frame and the little blue dot, which represents the center of the motion, we implemented a control system via finite state machine that decides whether or not we should move the camera. And our implementation consists of having such a move left threshold and move right threshold. And it's as simple as when the blue dot enters the blue, or the move left or move right threshold, it jumps to the next state in the finite state machine. However, there's a lot of more configurable parameters, such as how long the speaker needs to be in the frame, the thresholding values, X, Y. We're just using those. However, we can also take acceleration into account and various other parameters. And for the finite state machine, we actually are generating on the fly. We read out an encoded finite state machine from our key value store, and at runtime we turn it into an actual finite state machine. So this is one we came up with for our demo, and essentially every state has a left or right, or it has a left or right state, and it's possible actually to have no additional state it can go to if, let's say, you're at the leftmost position. And an example of this in actual practice is if, let's say, I'm in the middle frame right now. If I were to move to one side, the camera doesn't exactly know my exact intentions. So I could just be moving here to, let's say, present something over here. But if I'm in the hot zone, the camera will move to the next frame. So as a result, we implemented additional states where if, let's say, I'm over here, it'll zoom out a little bit and still get this entire frame in, but a little bit of the next frame. And from there, it decides if I move more here, I'm probably going to want to move to the other blackboard. However, if I move back here, then it'll focus back on the main blackboard. And as a result, even though it looks very similar, or it looks very simple, in our testing, it had very natural looking movements where it framed whatever presenter is moving, whatever presenter is moving in a very natural way. And as we mentioned, we build this up on the fly. So depending on room configuration, we can make this as complex or as simple as needed. And all this is actually implemented in a website. So instead of just showing you a static image, might as well show you the real website. So this is our computer running over there in room 910, I believe. But I just enabled camera polling. So as you can see, we disabled all thresholding, or all minimum thresholds for optical flow. So it's detecting a little bit of noise, and we have a little bit of motion in the frame. There's no presenter here, so I'm just going to manually disable the automatic tracking, and I can manually select which state before. So these are all filled in from our room configuration. So I can say, let's move to the right frame. As a result, it'll move to the right position of the frame. I can also manually specify the coordinates, so we can let's see who's playing or who's skipping this speech. Or I probably need to move a tiny bit more. Say 85 degrees. And I don't really see anyone. I can zoom in a little bit more. Oh wait, there's someone. Can deduct points from them. And this is completely accessible from any sort of device. As you can see, we're pulling images. It's a low frame rate, so we're actually capturing at a full 30 frames a second. But since we wanted to have this work on mobile devices, browsers, we're actually just implementing our own very simple video where we're pulling a new JPEG image around every four times a second. So we actually encode the JPEG image, store it in our key value store, and we have a CGI script that will actually upload the image data. And I think someone just logged in and started taking control. All right. So I'll disable camera polling unless. And with that, are there any questions?
So first of all, it seems to me you'll have some problem with sudden movement where you lose the person, then you don't know what to do. Like if I come into the frame and then I'm running over to the side faster than you can track me, you'll lose me, and then what do you do?
So two things in regards to that. The frame rate you saw up there, we're actually capturing a full NTSC 30 frames a second. So we're doing the processing within, we said 33 milliseconds just because that's 1 over 30 or 29.97. But we make the decision within a couple of milliseconds. So yes, if you are running, you will have a problem. But as I mentioned before, for our demos right now, we're just using simple, you're in this zone. But from the optical flow, if you saw there generates lines, we can actually calculate the acceleration, the velocity, and decide if, let's say it's a very fast movement, we should just completely transition to the next state, or from like middle to left blackboard. And in the case of someone running really, really fast, faster than the camera can move, then yes, we'll move them. We'll lose them. But our requirements weren't to completely replace the operator. It's to supplement them. So if you try to break the system, you probably can, but that's why there's someone there that needs to set it up and also work with it.
So if I understand correctly, you're running full Lucas Canada optical flow in full frame, getting up the vectors at every position, and then you're identifying unique feature points on which you know the flow vectors, and you do a centroid to get the point.
Correct.
What kind of feature detector are you using?
I believe it's fast.
facing.
Yep.
Did you test it? Because you mentioned at the beginning the requirements of illumination changes. A presenter, a lecturer in front of the screen with slides, all the time changing color, brightness, illumination, features, textures, images, and so on. If you put a person moving in front of that and you flip a slide, you're going to get a lot of mismatches because you will lock between the person and the screen image.
Right.
Did you test that in fine illumination conditions?
Yeah, we did test that, and we did get a little bit of that, but not enough to break the system.
Also, if you're in a slide situation, it's going to be different than a normal lecture where you have 3 blackboards, let's say. You usually want to have this, the PowerPoint in the frame at all times. So as a result, you can set up the room configuration so that it takes that into account. So that it'll always try to frame around the slides. And since when the slides change, it's a rapid transition all over the frame, the centroid should be in the center of that frame. Not always. No?
You have a lot of problems with illumination.
Well, we can demo it.
Yeah.
Considered allowing gestures to control talking. I can gesture this way to the camera.
That was actually one of the original iterations of the vision processing, where you could like make a fist, make a like open hand, and it would detect what type of gesture you were making. And we were going to do something with that where it knew what was in the image, but again, thresholding doesn't account for dynamic light changes very well. So filtering skin isn't much of a great thing either, because you're kind of far away from the camera. Yeah.
Have you been able to pilot this during a distance learning class here at UU?
Not yet.
Is it in the future?
Yeah. Yes.
Thank you.